Like I said, today begins part 2 of Unit 1. Part 1 was all about concavity, average rate of change, and polynomials. You can read the top of these notes. What type of function are we going to be focusing on in part 2? Rational functions. Now, rational functions, I know, gets glossed over, unfortunately, in Algebra 2 because of it happening during testing season at the school. So I am not sure how much about rational functions we know, so I'm going to teach it like you've never seen anything before. Is that okay? Yeah. Now, what is a rational function? I'm so glad you asked. Okay, so we've seen a rational function. We see what's happening. Here's some things I need you to know about it. A rational function is a function such that f of x over g of x, where g of x is not 0, meaning you have a polynomial on top and a polynomial on the bottom. The one I showed you on Desmos was simple. It was a 1 on top and a 2x on bottom. As long as there's an x in the denominator, it is a rational function. So these three functions here are all rational functions because if we zoom in, you don't have to write this down, but just look. What type of function is on top here in the numerator? Say again? I mean, is it even number? Yeah. It's just a plain number though, right? What kind of function is it called when it's just a plain number? Constant. It's a constant function on the top. That's degree 0. What kind of function is in the bottom? Well, okay. Well, like if it was only this, what type of polynomial is it? What's its degree? 1, which means it's a what kind of function? Looking for a word that starts with L? Linear. So we have a constant function on top, a constant function on bottom. That's a polynomial over a polynomial. What about the k of x? What kind of function is on top? Quadratic, degree 2. What kind is on bottom? Linear, degree 1. What about m of x? What's on top? Quadratic. Ooh, what about this one? Cubic. So as long as we have a polynomial on top and a polynomial on bottom, we have a rational function. Now, I told you earlier when we were looking at Desmos that we're going to be focusing on the horizontal asymptotes. Notice the word on your notes is not even horizontal asymptotes. What word have I used here on your notes? End behavior. The horizontal asymptotes, bless you, are going to tell us or teach us about the end behavior for rational functions. So same vibe when we did polynomials. You'll be writing limit statements for me to describe end behavior, but this really, really works well with what's called the horizontal asymptote because rational functions behave at the end of their graphs with their horizontal asymptotes. Now, this can be determined by two things, by the leading term of the numerator and the leading term of the denominator. So we're going to look at these polynomials separately. To look at the leading term of the numerator, I really need to make sure I'm focusing on the power or the degree of the polynomial in the top. For your notes, I'm calling that n for numerator degree, and then d for denominator degree. Those are things we're going to focus on. There are 3 cases when it comes to rational functions, and I'm going to teach you some acronyms that I think are super duper helpful. They're also really fun to say, that control all of the information that you need. Case number 1 is called BOBO. Yes, you heard me right. BOBO. BOBO occurs when the denominator degree dominates the numerator, aka the numerator degree is smaller than the denominator degree. What that means for us and why it's called BOBO is that the degree is bigger on bottom. Bigger on bottom. The last letter here tells you what the horizontal asymptote is. This is actually the number 0. So our horizontal asymptote for any BOBO graph is going to be y equal to 0. That's the horizontal asymptote. That's where the graph would be flattening out, which is exactly the one I showed you on Desmos when we started. You noticed it was not touching 0. It has a horizontal asymptote at 0. So all BOBO graphs, all bigger on bottom graphs, their end behavior is as follows. We would write the limit as x approaches negative infinity for the function f of x would be equal to 0, and the limit as x approaches positive infinity for f of x would also be equal to 0. Because we have a horizontal asymptote that is 0, it's going to control the end behavior. Your graph is going to get very, very close to but never touch 0, but it sure does approach it. That's what we're saying the limit is. It's getting closer and closer to 0. Never actually touching it. Same way you can't actually touch infinity, but we're getting close to it. That is a BOBO graph. Bigger on bottom 0. BOBO. The second case, okay, first case was numerator smaller than denominator or bigger on bottom. The second case is called botn, B-O-T-N. Botn stands for bigger on top. This happens when the numerator degree is bigger than the denominator's degree. It's bigger on top. The N in bigger on top stands for no horizontal asymptote. It does not have a horizontal asymptote. So if I asked, you'd be like, there's not one. I'll come back to this note in a second. The end behavior of the polynomial requires a little bit of work when you have a botn graph. The end behavior matches a polynomial with the properties of the leading coefficients, a over d, and the degree, n minus d. We'll see plenty of examples of this, so this means nothing yet, but I promise it will in a second. Your limit here, your end behavior, the limit as x approaches negative infinity for any botn graph for f of x, would either be positive or negative infinity. And the limit as x approaches positive infinity for the function that is botn is either positive or negative infinity. It does not have a horizontal asymptote, so the lines at the end, the arrows at the end, are either going to go off up or off down. And it follows a polynomial, like we did in the previous unit, that has a leading coefficient of a over b and a degree of numerator minus denominator. This means nothing until we see an example. I fully understand that. Hang on with me. The plus or minus? Yeah, no, that is a plus or minus. Now we're going to come back to this note for a second. If the degree of the numerator is exactly one more than the degree of the denominator, then f of x has what's called a slant or oblique asymptote. So it actually has an asymptote, it's just not vertical or horizontal, it's slant, it's crooked. Okay, I like to call these graphs botn by 1. So if you see that you have a bigger on top by 1, you have a slant asymptote.
I mean, he's got loss.
That's fine. I'll make another one. Thank you. Okay, so our botn, if you ever have a botn graph, bigger on top, you're going to pause because that one takes a little bit of work. Okay, because we might have a slant asymptote or you might just have end behaviors that both go up or both go down. The third case is called BETC. B-E-T-C. This happens when the bottom degree is equal to the top. BETC. Bottom equal top. Again, that means that the numerator degree is the same as the denominator degree. And when this happens, the C tells us that we are going to take the coefficients of the top and bottom and divide them to find our horizontal asymptote. BETC. Bobo, botn, BETC. Now this horizontal asymptote, kind of like Bobo, controls the whole graph, which means that your limit statements here, the limit as x approaches negative infinity for f of x, is going to be equal to that ratio of numerator leading coefficient divided by denominator leading coefficient. Same thing for the positive side, as x approaches positive infinity, it would just be equal to that a over b. So this part, real simple. If you find the horizontal asymptotes, you immediately know the end behavior. The graph will always get close to but never touch those horizontal asymptotes as you zoom right or left, as we approach negative infinity and positive infinity. So again, the only one that might cause us to pause should be our botn graphs. We have Bobo, botn, and BETC. Bobo is bigger on bottom, horizontal asymptote is 0. Bigger on top, there is no horizontal asymptote. Bottom equal top, divide the coefficients. So let's just practice right now. We're just going to identify whether it's going to have a horizontal asymptote, slant asymptote, or neither. We're not going to actually do the end behavior just yet. We're just going to determine these asymptotes. So we don't have to do much work. I know we just practiced factoring. And eventually, I do want your instinct to think, I should probably factor this, but we're not factoring today. We are just comparing the exponents. What is the leading exponent on top? What is the leading exponent on bottom? Is this graph Bobo, botn, or BETC? BETC. So we're going to write down BETC for ourselves because we're remembering that this is BETC. BETC tells me that I need to divide the coefficients. If I was writing down that this has a horizontal asymptote, it occurs at y equal to 3 over 5. Where did I get the 3 and the 5? The leading coefficient, yes. I just look at the leading coefficient of the polynomial on top, 3, and the leading coefficient of the polynomial on bottom, 5. Boom, there's my horizontal asymptote. This graph would flatten out at 3/5. Horizontal asymptote, thank you for asking. Horizontal asymptote. That's a lot of letters, so I just write HA, but yes, horizontal asymptote. For letter B, again, we ask ourselves Bobo, Botner, Betsy. So what is the degree of the top? What's the degree of the bottom? 2. So where is it bigger? It's bigger on bottom. Bigger on bottom, which means that the horizontal asymptote is going to appear at y equal to what? 0. That's it. This graph flattens out at 0. That's maybe the wrong phrasing to be using, flattens out. But at the end, you're getting closer and closer to 0 on the right and left sides. What about this guy? Let me just ask this one. Is this Bobo, Botner, Betsy? Botan. Okay, Botan, we pause. Because Botan does not have a horizontal asymptote, but we have to ask ourselves, does it have a slant asymptote? How much bigger on top is it? It's by 1. So this is actually a Botan by 1. It's bigger on top by 1. That means that it does have a slant asymptote. We're not going to find the equation of the slant asymptote just yet. So we're going to say there is not a horizontal asymptote, but there is a slant asymptote. Okay, so again, if it's Botan, bigger on top, and specifically bigger on top by 1, we know it's a slant asymptote. Bigger on top, no horizontal. Bigger on top by 1, there is a slant. Can I challenge you guys to find the horizontal asymptotes of D, E, and F here? Let's see if we got it. Hopefully I'm not cutting off your thinking, but let's see. For number D, is that one Bobo, Botner, Betsy? Betsy. Betsy reminds us that the bottom degree equals the top degree. So we divide the coefficients. This one has a horizontal asymptote, and it appears at y equal to 1/2. If you said 4/8, same thing, I reduced my fraction. You should probably reduce your fraction as well. But 4/8 was correct, yes. Okay, how about E? Is that one Bobo, Botner, Betsy? Bobo, we have degree 2 in the denominator, degree 1 in the numerator. That's a Bobo, which means we have a horizontal asymptote, and it appears at y equal to 0. That's the boundary. How about for letter F? Bobo, Botner, Betsy. This is also Bobo. And Bobo, since that second O is actually a 0, again, it has a horizontal asymptote at y equal to 0. Now, on the back of this paper, don't flip over yet because we're going to play a Kahoot before we go. We're going to take these ideas and we're going to actually translate them into end behaviors, because right now, all we're doing is finding the horizontal asymptotes. But that's step 1 into determining the end behavior of the function. But yes, we are going to play a Kahoot just to make sure we understand Bobo, Botner, Betsy. It's a quick Kahoot, so go ahead and open your computers. Let's log in. Now that we've practiced identifying the horizontal asymptotes, let's go ahead and translate those horizontal asymptotes into end behaviors for these functions. Again, I think it's easier to start off from a graph so you can see what we're even talking about here. So we have the graph of k below. Do you notice that we have a horizontal asymptote floating through the graph right here? What number is that horizontal asymptote occurring at? 2. That is the end behavior. If you look on the left side of the graph, that arrow on the left side of the graph is getting closer and closer to 2. And if you look on the right side of the graph, that arrow, I know it's not there, we're drawing it in, is getting closer and closer to 2 as well, which means we can write the limit statement for the graph of k as follows. We can say the limit as x approaches negative infinity for k of x is equal to negative infinity. What is equal to 2? What am I doing? And the limit as x approaches infinity for k of x is equal to 2. It's the same on both sides because we have a horizontal asymptote that the graph's getting closer and closer to on each side. We see that? So on B, the graph of m of x is right there. What number are we getting closer and closer to on m of x every time? Say again? B. Yeah, on B. -1. See how both sides are flattening out at -1. They're approaching -1 on the left, and we're approaching -1 on the right. It's getting closer and closer to those numbers. So we can write the limit statements with that particular number. This would be the limit as x approaches -infinity, this time for m of x, is equal to -1. And the limit as x approaches positive infinity for m of x is also equal to -1. We're getting closer and closer to that horizontal asymptote, which appears at -1. Now a little bonus question. Would these graphs, if we saw their equation, would they both be Bobo, Button, or Betsy? They would be Betsy. Why would they be Betsy's? Because it's equal to a number that's not 0. If it's equal to 0, that's Bobo. If it's equal to positive or negative infinity, that's Button. If it's equal to a number, that's Betsy. So these would both be Betsy equations if we had their equation. Now we're not always going to have a graph, so we do have to think about Bobo, Button, Betsy, the horizontal asymptote, to answer for an equation. Let's look at C. Is this one Bobo, Button, or Betsy? Betsy. All right, so we know that it's Betsy. The bottom degree equals the top degree, so we have the coefficients. If we were just writing down the horizontal asymptote, what would it be at? Y equal to 2/6, which reduces to 1/3. Amazing. If you can do all of that, you can write the limit statements, because that horizontal asymptote is the number that the graph is flattening out to on the left and on the right. So we use that number in our limit statement. The limit as x approaches -infinity for f of x would be equal to 1/3. And the limit as x approaches positive infinity for f of x would be 1/3. The horizontal asymptote is your end behavior. That's what it is doing for the graph. You're getting closer and closer to those values on the left and the right side. Do we follow? Okay, walk me through D. What should I ask myself first? Yes, I heard 3 and 2. What are we asking ourselves there? We're looking at the 3 and the 2. The bottom one's bigger, which means that this is a Bobo graph. What does that mean? I think I heard that through all the mumbling there. The horizontal asymptote is what? 0, which means the limits will both go to what? Well, yes, both infinities will be equal to what number? 0. So we can write all of the limit statements. We say the limit as x approaches -infinity, that's the left side, of g of x equal to 0. And the limit as x approaches positive infinity for g of x also equal to 0. Just as a side note, there were some people on our test, I don't think it was this class, who lost out on points on the limit statement question in the free response because it asked for the limit of g and they put f. That's wrong. That's the wrong statement. You have to make sure these letters match up. So make that really a point for you. Now what about E? That's Button. Okay. Especially when we're writing limit statements, we're going to pause on Button because we need to think. It does not have a horizontal asymptote. Does this one have a slant asymptote? Yes, it will have a slant asymptote. Cool, great, awesome. Now here's how we find out the end behavior, because the slant asymptote tells me that it's either going to be positive or negative infinity, and we need to figure out which one it is. So we think about this graph in the following way. We're going to tell ourselves that the end behavior of this graph is going to match a polynomial that has a leading coefficient of -3/1 and a degree of 4 minus 3. Where did I get all of that stuff from? Where did I get the -3/1 from? Yeah, the leading coefficient. You see how that's -3 and 1? Okay, where did I get the 4 minus 3 from? Yes, I'm just subtracting the numerator degree minus the denominator degree. So if I actually do this quick little math problem, this is -3 times x to the first power. There it goes. Okay. So my question for you is, if I were to ask you, not a rational function, but if I were to ask you the end behavior of this polynomial, not this one, This one. What is the degree of this polynomial? 1, odd. What is the leading coefficient? Negative. So we'd have a leading coefficient that's less than 0 and a degree that's odd. What does that look like for end behavior?
As x approaches negative infinity,
It's going to be opposites because it's odd. What does your right hand? Your right hand going up or down? Down. So quickly you're doing kind of like this, yeah?
Yeah.
Oh, thank you. We found the hall pass. Okay. So this is the degree, this is the end behavior of that polynomial. That means it's the end behavior of our rational function. So the limit as x approaches negative infinity for h of x, we have an arrow going up, it's positive infinity. And the limit, I spelled limit wrong, limit as x approaches positive infinity for h of x would be negative infinity. Again, where did I get this from? Here. This positive infinity is because of this. This negative infinity is because of this. I went to school for a long time. Thank you for the compliment. Okay, I'm assuming there's going to be questions. Can someone ask a question before we go? Because we hadn't seen something like this happening before.
I'm confused all around.
For this problem, or do I need to go back a little bit? Okay, let's pause for a second. Let's go back here. When we're determining end behavior of a rational function or determining the horizontal asymptotes, you ask yourself, is the function Bobo, Botner, Betsy? Meaning, is the degree of the function bigger on top or on bottom? For this one, you see how they're both degree 3? That means the bottom equals the top. That's Betsy. Betsy tells me to take the coefficients and divide them. That's what the C means. 2 over 6 is 1/3. So that horizontal asymptote of 1/3 is the same number I use here in my end behaviors. That's what the graph will flatten out to, like the graphs right above this. That would be the little dashed line if we were to graph these. Same thing goes for the middle one. We compare the exponents. Where is the exponent bigger? On the bottom, so it's Bobo. Bigger on bottom. Bigger on bottom means that this graph has a horizontal asymptote that is 0. The last O in Bobo is actually a 0. So this number here is here. We don't have to look at the coefficients because it's Bobo. The bottom dominates the top. For the last one, because this is Botten, we have to pause. Botten tells me there is no horizontal asymptote. Okay? So I have to think for a second what its end behavior might be, because it's not going to have a flat line that the graph gets close to on the edges. What we do is we look at the leading coefficient of top and bottom and the subtraction of the degrees, top minus bottom. If this was a polynomial, it would just be negative 3x, which is a negative leading coefficient and an odd degree polynomial. When we studied polynomials, when we did the Miss Quigley says with our arms, negative or leading coefficient being negative meant my right hand goes down. Odd means my left hand goes up. So that's the same end behavior we have now for this rational function. It follows from the little shorthand here of just the leading terms. The ratio of the leading terms is what that's called. Better? Okay. Cool. Let's focus in for a second on slant asymptotes, because this function right here actually has a slant asymptote. Did you notice that this is bigger on top by 1?
Yeah.
It has a slant asymptote because we have a degree function that looks like a linear function at the end. That's what we're looking at for end behavior. That means it's actually a slant asymptote. So let's focus in a second. A slant asymptote occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator, aka this is Botten by 1. Bigger on top by 1. If it's bigger on top by 2, it does not have a slant asymptote. If it's bigger on top by 3, does not have a slant asymptote. This only appears when it's bigger on top by 1. Okay, Now, we're not necessarily, at least today, going to be finding the equations of the slant asymptotes. What we're going to be finding is the equation of a line that is parallel to the slant asymptote. This is helpful because it does help us on a graph see that we found the right end behavior, because it would be parallel to the actual lines that you have, the curves that you have. Now, this is exactly what we did above. When we were finding that fancy end behavior for the bottom graph, didn't we take the ratio of A over B? And the power was numerator minus denominator? But if it's bigger on top by 1, that means that my numerator minus denominator would give me the number 1. So all we have to do when we know there's a slant asymptote is realize that it's going to be parallel to the line y equal to coefficients times x. So a question you might see, just to put this in motion, is which of the following rational functions has a slant asymptote parallel to the line y equal to 1/2 x? Okay, first things first, for something to have a slant asymptote, it has to be bigger on top by 1. So let's go through here and just eliminate ones that are not bigger on top by 1. For letter I, this is bigger on top by how many? By 1. Okay, we keep that one. How about number 2? Bobo, Botner, Betsy? Bobo. All right, Bobo, not going to have a slant asymptote. Goodbye. What about number 3? Bobo, Botner, Betsy? Botten. And Botten by how many? By 1, because it's 2 on top, 1 on bottom. So it's Botten by 1. We'll hang on to that one. Number 4. It's Botten, but by how many? Ooh, is that going to have a slant asymptote? No, get rid of it. Only Botten by 1 has a slant asymptote. They have difficult end behaviors, but these are the only 2 that have slant asymptotes. Now we need to figure out what it would be parallel to. What we do here is we just look at the ratio of the coefficients. What is that ratio right there? 3 over 2. So this one would have a slant asymptote at y equal to 3 over 2x. Sorry, I said that wrong. It would have a slant asymptote parallel to the line y equal to 3 over 2. That's not necessarily its actual slant asymptote, but it's parallel to it. Is that what we wanted for this question? No, so we're going to get rid of that one because that part's wrong. What about number 3? If we do the ratio there, what's the number on top? What's the number on bottom? 2, which means we will have a slant asymptote that is parallel to y equal to 1/2 x. This is only for Botten by 1. Say that one more time. If it's Botten by 2, it does not have a slant asymptote. So you would say no horizontal asymptote, no slant asymptote.
So on the first one,
This one?
yeah, why is there only x? So
Here in the slant asymptote?
yeah.
Because we're not actually finding the actual function, because you would have to do long division to find the slant asymptote, we're just finding a line that would be parallel to it. So you'd end up with the same slope and a different y-intercept.
It's a linear line.
Yeah. It'll always have either a positive linear function or a negative linear function that it would be parallel to. That was a great question. Y'all want to do another Kahoot just to see if we've got it down? Yeah, let's do another Kahoot. That'll end our lesson for today.